Let's start. So in the last class, we looked at how to do this digital calibration in pipeline ADC or in general any ADC. I'll briefly summarize the discussion and we'll move on. So the deal is this: in any calibration, the basic steps you follow are similar. The first step is this: say you have some circuit. This could be your ADC or any circuit. So ideally, let us say the output is some V ideal. If there is some non-ideality, and remember this non-ideality is what you wish to correct through calibration. This non-ideality will manifest itself as some non-zero voltage, let us say some non-ideal voltage at the output. So the first step is to somehow reliably sense this non-ideal portion of the output that exists, right? And this can be sensed in different ways, and that's what gives rise to different techniques. In the last class, we saw a couple of them. One was where you inject a dither sequence in the form of a pseudo-random noise, and the way we reliably sense the presence of this pseudo-random noise at the output was through correlation, right? So that is one way in which you do so dither and correlation. And the second trick we saw was to have this split ADC structure where the same input is given to the two guys, and here the non-ideality is a mismatch between these two. So getting this non-ideal portion in the output was even trivial here, so just take the difference between the two, right? But you can also come up with other ways to do this. The second step is to somehow use this information about the non-ideal voltage and do some corrective action in the circuit by tweaking an appropriate parameter so that this guy reduces. And for that, almost all calibration techniques use the same underlying principle, which is the following. So you have this non-ideal voltage, you want this to go to 0, so you basically compare it with 0, get an error signal, and you want this error signal to go to 0, you give it to an integrator, right? And then based on the integrator's output, you do some corrective action in the circuit. I'll just say you do some corrective action, that is you change some parameter in the circuit, appropriate parameter, so that this reduces. This essentially is a negative feedback system wherein you exploit the fact that if you have an integrator, the DC at the input of the integrator, what will this be? It will exactly be 0. Okay. See, I'm sure you have learned about gradient descent, LMS in detail in other signal processing and machine learning courses, but I want you to appreciate the fact that all of this gradient descent and LMS business, they all are based on this negative feedback principle. Right? That's the underlying thing, and that's what make those things work. And I mean, as we discussed, this is all done in the digital domain. So although I have put it as an integrator, this is a digital accumulator. So essentially you have an adder like this. So wherein you feedback so you keep adding the incoming input to existing output and do this. And also this calibration business need not be operated at the same speed as your original circuit. You can run it at a much slower rate to save power. Okay. So that is about this calibration, and now we have seen most of what you need to know about pipeline ADCs. So as you know, in pipeline you can take multiple low resolution ADCs, stitch them together in an appropriate fashion to improve the resolution. But the issue in pipeline is you have all these non-idealities. So to get higher resolution, you have to do extensive digital calibration. That's the only option. So let us say if we can do something better than this. And for that, let's look at how we came up to this pipeline ADC. So if you recollect, we started off by considering a normal ADC. So in a normal ADC, we have the input which is getting sampled, and then we quantize. How do we model the quantization? You just assume that we are adding some quantization noise, and I'll assume that input is all sampled. I will not keep drawing this sampler again and again. This is all discrete time. Okay, so I'll directly write this as, let's say y of it. Okay. So in a pipeline ADC, what was the basic line of thought which we extended?
Remove this Q of n.
Yeah, how did we remove Q of n? I mean, just in simpler words, right? What did we do to remove Q of n?
Separated from the
We subtracted q of n here, right? This is what the basic principles, right? And of course, to get Q of n, you have to subtract this guy and this guy, right? This guy is digital, this is analog. So what did we do? Yeah, we put a DAC. So we put a DAC here and then took the difference at another ADC and did all this. That's what gave rise to pipeline. Now let's say I don't want to do that. Okay. But the final goal is same, right? The idealistic goal I have is to make sure that at the output I don't have any quantization noise. So which means I have to go and subtract this quantization noise for sure, right? So this is an ADC, I have access to these 2 points only. In the pipeline ADC, I subtracted the quantization noise at this point. Is there some other place where I can subtract the quantization noise?
I can subtract it before and then
Yeah, I can add it here also, right? I just have 2 points that I have access to. In pipeline, I did this in the digital domain here. I can as well try to do it here. At least in principle, that sounds reasonable. So let's see what happens. So what I'll do is this. So here, I will go and say this is Q of n. And the usual convention is to call the input to the quantizer as y of n. So I'll call the actual input we are digitizing as some u of n. Okay. So now I need to extract q. So what do I do? How do I find q? I mean, if I find q, I can do this correction. But how do I find q? I mean, we did the same, right? How did we do in pipeline ADC?
we found that using that.
Yeah, we first put a DAC here and then took the difference. That's the only way in which you can do, right? Q is not known to you.
Yeah.
From the given ADC, that's what we can do. So let's say I put a small DAC, visually small looking DAC, and then let us say I took this difference. What do I get here?
Minus q.
No, look the,
Y. Oh, yeah.
this is y plus q.
Yeah.
I just exactly get q.
And Q of n.
I need q here, so I'll simply go and connect it. Fine. So what will be this signal y of n? Let me push it here. What is this y of n here?
Q of n plus Q of n.
No,
Minus of q.
minus of q of n. So if I look at the final output v of n, what is that?
Q of n.
Ah, that seems crazy. It simply completely eliminated quantization noise. So what's the issue?
Now we are subtracting it.
We can subtract it. This is the ADC. This is analog. This is digital. I put a DAC. So everything here is analog, right? That issue we had in pipeline ADC is not there here. But there is some other catch for sure, right?
But in pipeline ADC also we got this only, right?
But we didn't subtract it here, isn't it? We took this guy and subtracted here.
But both conceptually both are same, right?
Both are same, but in pipeline ADC we needed to have one more ADC here, isn't it? In pipeline ADC, we decided to subtract the quantization noise at the output side. Output was a digital, so this had to be digitized further and then corrected. And here we put a gain to have full scale.
Full scale, yeah.
So now I don't need a second ADC. I'm reusing the same ADC and doing it, right? And looks like conceptually this is fine, right? So what is the catch?
Means we cannot start giving Q of n randomly, right? Means
We're not giving it randomly, right?
not randomly, but okay.
Okay, look at this, right? So what I'm saying, I have the ADC input, I have the output. So I get the quantization noise and then immediately subtracting it from the input and then digitizing it. Does it seem reasonable or no?
Do you think it will?
I mean, what I'm doing, see, I am going to, this is basically an ADC, I have to digitize it. What I'm saying, the input I'm giving to the ADC for digitization is the input minus the quantization noise in the current cycle.
Yes.
But without digitizing, how will I know the quantization noise? See, the ADC first has to sample, digitize. Only after it has made the digital data, I can know what the quantization noise I have added. So only after I get that information I can subtract it.
Means you may use that, then you will have q of n, this will be q of n minus 1.
Exactly. So I cannot do it instantaneously, right? So here I am saying that even before I digitize it, I know what is q of n and I am subtracting it. That is practically, that is that is not following causality simply. So in this entire business, I will have one clock cycle of delay. Is that clear? So I will digitize data, get what q of n is, and I can use that information only in the next clock cycle.
Like as an estimate of.
Yeah. So this is going to have one clock cycle of delay. I will model it as Z inverse. Is that fine? Z inverse models one clock cycle delay. Okay. Cool. So now let's rewrite what we get. What is the signal here? So this is q of n. So I mean this point is q of n. This is q of n minus 1. So what is this guy? So what is the final output I get? Plus q of n I will have minus q of n minus 1. If I just use the ADC, I would have just gotten the input plus quantization noise. If I do this business, seems like I am getting q of n minus q of n minus 1. So let us see if it gives some improvement, right? Of course, in time domain, it looks like I am not able to get any intuition. So in time domain, if we can't get anything, what do we do? Right? Same thing in real life. If you don't get pocket money from your mom, who do you ask? That's all. So let's resort to frequency. I'll take Z transform. So this is U of Z plus what do I get? Q of Z into 1 minus Z inverse. Okay. Let me also write it in frequency, Fourier transform. This is U of e power j omega. One minus e power minus j. So let's quickly plot and see how the spectrum is going to look like. So if I just look at the quantization noise, how will it spectrum look like? It's going to be flat. So if I sketch this guy, sketch it properly. It's omega. Let us say this is S Q of e power j omega. So it's going to be flat like this from 0 to pi. Single sided path spectral density. Okay. And what will be the mean squared value of this quantization noise? Mean squared value or the variance of the quantization noise, what is that? No.
Delta square by 12.
Delta square by 12?
Yeah.
You corrected. So this is, this is delta square by 12. From the power spectral density, how will I find this mean squared value? Mean squared value is basically the power, right? Yeah, it's area, but actually if you, strictly speaking, there's a scaling factor of this. And then the single sided power spectral density. So I'll say this is basically divided by 2 pi. So that this area directly gives me the mean squared value. Okay. So this area of this rectangle is delta square by 12. So what is this value? The area is delta square by 12. What is that height? Delta square by 12 pi. Fine. So I'll directly write it here. Erase it, it's not needed. I'll just say SQ of e power j omega by 2 pi. It's constant and it's delta square by 12 pi. Fine. Cool. So next let's look at this fellow. So how will be the power spectral density of, let's say I call this QF, filtered version of e power j omega, filtered version of quantization noise. So if I look at the spectrum of this guy, what will this be in terms of power spectral density of this?
At the square of this term, the mode of.
Think about it. I have Q. Looks like it goes to a filter with a frequency response 1 minus e power minus j omega. Or let us say some h of e power j omega.
S of SQ of
SQ into
the mod of this whole
magnitude squared of the transfer function, right? So is that fine? So I'll directly write it. I'll erase this. So this is going to be SQ of e power j omega times magnitude squared of this transfer function. So again, let me say this is 1 by 2 pi, or let me write it a different line. One more undo. Okay. So which means if I write this SQF of e power j omega, what will this be?
1 by 4 pi square. No, sorry, 1 by 2 pi.
I'll have 1 by 2 pi here, and this guy is already delta square by 12 pi. So this is delta square by 12 pi times magnitude squared of this transfer function. Let's qualitatively sketch how this is going to look like. At omega equal to 0, what can you say about this guy? 0. So let's say this is point. At omega equal to pi, what happens to this guy? It's 2, but this is magnitude squared, right? 4. So at omega equal to pi, it does somewhere here. Maybe it's not drawing to scale, but let's say it's. Now let us say for small omega, I mean small is a relative term, I am loosely using it. For very small values of omega close to 0, what can I approximate this guy as? J omega. So magnitude squared of this is? So if I try to sketch it for very low frequencies, it is going to go as omega square. Basically it might do this, something else.
How do you know that it will be like this?
I mean, this is just qualitatively I have drawn, but this is how it will look like. I mean, you know these values, right?
Yeah, that we can okay.
Cool. So now look at this thing and tell me, this is a high pass filter or a low pass filter? High pass filter, because I had this flat quantization noise. After I passed it through this filter, the low frequency content is greatly reduced and high frequency content is boosted. So this is essentially a high pass filter. And this act of taking the quantization noise or any noise and shaping its frequency spectrum is often referred to as noise shaping. So this is called noise shaping. And in particular, this architecture that does this noise shaping is often called error-feedback noise shaping structure. For obvious reasons, we are feeding back the error and doing this thing. Okay. So okay, now at least the spectrum looks beautiful and we have given a cool name, but we should at least see if this is giving any benefit, right? So let us see if this is indeed beneficial. So let me copy paste this. Yeah. So let us say the sampling rate in my system is fs. So let me write it here explicitly. Sampling rate is fs. That is, in the signal, in the original system, I am going to sample my signal at a rate of fs. Okay, this is u of t. Don't confuse it with unit step. This is a messed up notation, but yeah. Cool. So now this is omega. If I map it to continuous time frequencies, this will correspond to what frequency? 0. Pi will map to what frequency in continuous time? Fs by 2. So sampling rate is fs, so this will map to fs by 2. Right? Now I know that if I sample at a sampling rate of fs, my signal can have this entire bandwidth from 0 to fs by 2. Right? So now look at this quantization noise spectrum and tell me, if I were to get any benefit out of this entire business, how should I be choosing my signal bandwidth to be?
Between 0 and second option.
At least I hope you are getting it, right? So we want to make sure that the output quantization noise effect should be smaller. At low frequencies, the quantization effect is smaller, or at high frequencies it is smaller? Low frequency. So we try to choose my input bandwidth to be low frequencies. So let us say I choose it to somewhere here. Let us say this is 1/mth of the maximum frequency. So this will map to what? Pi maps to fs by 2. Pi by m will map to. So this is how I will choose my signal bandwidth to be. Okay. And if I choose my signal bandwidth to be fs by 2 times m, what would be the Nyquist sampling rate, or what was the rate at which Nyquist recommended us to sample? 2 times this, which is fs by m, but we are sampling at fs, right? So what kind of sampling are we doing? I mean, we are oversampling, undersampling, oversampling, and this ratio of the actual sampling rate by the Nyquist, Nyquist sampling rate is called oversampling ratio. I think we already saw this when we discussed sampling, often abbreviated as OSR. So the bottom line is, noise shaping alone is not enough. You have to combine along with oversampling. Only then you can get any benefit out of this overall thing. Okay. So this is basically oversampling plus noise shaping. Right. So what we do is this: first we take my signal. The signal has a small bandwidth, but we oversample the signal at m times the Nyquist sampling rate, and then we do this business. If I do that, my quantization noise will be high pass shaped like this, and within my signal bandwidth, the effect of the quantization noise is really small, right? And remember, this is only, the quantization noise is reduced only in this band. Okay, outside this band it is actually higher, right? And in fact, if you look at the overall quantization noise, right, or maybe we can look at it. So let's say I want to find the overall quantization noise here. I am trying to find the overall quantization noise power after doing this noise shaping. How will I find it? I want to find the noise power of this guy. How will I find it? I have to take the area under this curve, right? And I already have the expression, so let me use it. Yeah, this is the expression. Let's quickly do that. Good. So I have to integrate this from 0 to pi. So I have delta square by 12 pi. It's a constant, so I'll remove it out. Push it here. Into magnitude of this guy. So this is going to be the mean squared value of the filtered quantization noise. I'll just write as QF square. So how will I solve this? And of course I can do this, but is there something you can do to simplify this?
I know one thing, but I can convert e power minus j omega.
I mean, let's say without solving this integral, is there something? If I say the name Parseval, does it ring a bell? Parseval. No? Parseval. Yeah, I mean, right. So that's basically this, right? If you have 1 by pi, let us say.
Okay.
You remember Parseval? He's not your hostel room neighbor, but you still remember him, right? So this is equal to what? What is this equal to? I mean, you can do this in time domain, okay? So I mean, now I have x of e power j omega as what? So what is x of n? Sorry. Okay.
Delta and delta d, right?
Okay. See, if I have x of n, how will I find x of e power j omega? How will I find the Fourier transform?
Do integral e to the power minus.
No, but this is a discrete time, right? How will I do integral?
Discrete time.
Summation n, x of n
into e to the power minus j omega.
So if I do it, I'll have x of 0 plus x of 1 e power minus j omega, so on. So here I have 1 minus e power minus j omega. So what is my x of n? That's all, right? This is actually pretty straightforward because you already have the thing expanded in powers of e power j omega. You can just look at it and see. This is basically delta of n.
Delta of n minus plus delta of n minus 1.
Yeah, that's all. Same thing. Minus, yeah. Fine. So now I know x of n, that is basically 1 and minus 1. So if I do this, what do I get? 2. So I know this guy is 2.
With pi is 2.
Yeah, with pi it's 2, right? So my total quantization noise power after filtering, how much is it? Two times delta square by 12, right? To start it off, I had only delta square by 12 from here. After doing this filtering, the overall noise is higher, right? But only if I look at this portion, it is small. So I should not be, after doing this noise shaping, it is not as though my job is done, because only within this signal bandwidth it is small. I have a whole bunch of garbage outside my signal bandwidth. So what should I do? I should filter them out because my signal is only here. I don't need any content in this band. So I can put a low pass filter and filter it out. Okay, that is something we have to do. So let me copy this first. So the output, as we just discussed, we have to put a low pass filter. And remember, the output here is a digital data or analog data? Digital data. So what kind of low pass filter will it be? Analog low pass filter or a digital low pass filter? It will be a digital low pass filter. So it's easy to design. So it's digital. See, how do you, let's come to that when we look at it. Okay. So at the output of this ADC directly, if I look at the spectrum of the quantization noise, it's looking like this. Let us say this is my signal bandwidth of pi by m or fs by 2m. After filtering, how will it look like? Too much of stuff. Just a second, let me make some space. Yeah. After filtering, how will it look like? I am going to only pass this portion. Yeah, so only that initial portion will be there and so on, right? So again, this frequency is pi by m or fs by 2m. Cool. And remember, after doing this guy, I find that if I look at the output here, I don't have any content beyond fs by 2m. Earlier at least I had the noise, so now there is absolutely no information beyond fs by 2m, right? And here my sampling rate is fs, so here also the sampling rate is fs, right? So I find that at the output there is no content about beyond fs by 2m. So what can be the sampling rate now? It can be fs by m, right? So what is usually done is after this you reduce the sampling rate, and that is done by what is called downsampling. That simply discards sample, right? Let us say this is giving you x of 0, x of 1, x of 2. It only picks the 0th sample, mth sample, 2mth sample and so on. It discards all the other samples. This way you reduce the sampling rate. So here at the output I'll have, so if my input, if you recollect, it had a bandwidth of fs by 2m. Okay. What I do, I initially oversample it and then do this noise shaping. This way I push out most of the noise outside my signal bandwidth, right? And after doing that, I filter off this guy and then I bring the sampling rate back. Okay. I mean, of course, I can directly take this guy and do it. That is also same. But since there is no content beyond fs by 2m, it is not necessary to process this data at fs. right? You can bring the sampling rate down so that the succeeding digital circuits can operate at lower speed. Otherwise, functionally there is, in terms of performance, there is no other degradation. So, bottom line, noise shaping, you can think of it like this, right? You have garbage at your home. What do? Push most of the garbage to your neighbor, right? And remember, your neighbor must be good to filter it out later. So if you have a good neighbor and you push your garbage to his house, and if he filters it out, then overall you get something. So here we have a good neighbor in the form of this low pass filter. Okay, cool. So now at least qualitatively we can see that after doing this, the quantization noise present is very small, right? So I can go and choose a large value for this oversampling ratio. So which means the quantization noise present at the output will be even smaller. Basically, if I keep increasing m, now I am here. If I increase m, I will be here somewhere. So the quantization noise will be even smaller. So I can keep increasing m and reduce the effect of quantization noise. So if the quantization noise power reduces, what can you say about signal to quantization noise ratio? Increases. Effective number of bits increases, right? So what you can do is this. In practice, you often do this. This is an ADC, remember, so I'll mark it like an ADC.
This can be 4-bit.
It can actually be a 1 bit, right? This can be 1 bit ADC. Simplest thing you can do is 1 bit. And I can choose a large enough value of m so that within the signal bandwidth, the quantization noise power is small, and that gives an SQ and R corresponding to 16 bits also, right? So what I am saying is I can choose a large enough value of m so that within my bandwidth I have really small quantization noise, and that quantization noise power corresponds to an effective number of bits of 16. So I am claiming here I can get 16 bits, and we can do it actually. So I am saying enob of 16. But that should make you ask some question. What is the question? Huh? Okay, I am using how many bit ADC? So how many bits I can get from here? 1 bit. But I am claiming I am getting enob of 16 bits. So we have two statements. One is this, right? I just have 1 bit here. That is true. Second statement is I find that if I have large enough m, I can choose an appropriate value of m so that the quantization noise power in that band is very small, and I can get an SQ and R corresponding to 96 dB or like 16 bits. That is also true. Both statements are true. So what is that bridge connecting the two statements? How are we getting that extra 15 bits? So this is also true. Here the input is only 1 bit. But at the output, I am saying we can get an effective resolution of, let us say, 16 bits. Which block do you think is giving that extra bits?
Less than m.
This downsampling by m, it is just a downsampler. It just discards samples. It doesn't do anything, right? Incoming samples come. It just picks every mth sample and throws it at the output. So what is the other block? Huh? See, logically speaking also, or first let's look at how it happens. So it's a digital low pass filter, right? And remember it's an LTI filter. If let us say it has, I'll use this guy. If let us say it has input of x, it has an impulse response of h. How can I find its output? Convolution sum. So it's going to be some x of n minus k. Now remember, this is a digital low pass filter, which means this operation must be done digitally. And this operation is simple multiplication and accumulation, right? I am multiplying and adding. I just need a simple math block, multiply and accumulate block, right? And as I mentioned, this has to be done digitally, which means both these guys must be digital. My input x is the 1 bit data.
H of k will be your
Yeah.
next statement.
So this will be 0 or 1, it's fine. Now I have this impulse response, right? Now ideally if I look at the impulse response, do not draw the y-axis. I'll just. Sorry. Okay. Let's say I look at the impulse response. Let us say ideally, say ideally the impulse response looks like this. Something like this, okay? Right? Now, let us say one of the impulse response values is 0.29316740 something. It's going to be really, like some value, but we have to represent it digitally, which means I cannot represent it with infinite precision. I can use only finite bits for representing it. Now, let us say I use very small number of bits for representing it. So, let us say I round it to 0.29, right? The actual impulse response I have is this. So, same way I will be making some error everywhere. Okay. So, ideally let us say the frequency response look like this. So, this is pi by m. So, within this band it allows everything completely and then sort of filters it out. Now, I will not be able to represent this with infinite precision. I use very small number of bits to represent. So what can happen is this, the filter's frequency response can sort of get distorted, right? So if this happens, I will not be able to reject this guy fully. See, remember our neighbor has to be good. So I have to filter out the out of band noise. That is really crucial in finally ensuring that there is no noise here. So if I don't design this filter properly, at the output ideally I should have gotten something like this, right? But instead probably I will get something like this. I still can have some noise outside my band. So the overall quantization noise power will increase now, right? So I cannot use really small number of bits for representing this. I'll have to go and find what is the minimum number of bits I need to use to represent my impulse response so that I get a reasonable filter frequency response, and that filter's frequency response must be able to attenuate this guy to sufficiently small amount. So after filtering, if I look at the overall noise power, that should be close to what I get in the ideal case. So that is how I have to decide how many bits I have for this filter. So now logically tell me at the output, let us say I want an enum of 16 bits, how many bits I should allocate for this guy? Input is a 1-bit data. So how many bits I can allocate? I mean, just take one guess, right? There is no right answer. 15, at least 14, 15 bits. 15 bits at least makes sense. And in practice, it can be even higher actually. Okay. It all depends on how good of a filter you have, right? So at the output, it is not uncommon actually to find that you have 18 or 19 bits, but it corresponds to an enum of 15 or 16 bits. I mean, this is again like redundancy we have been looking at in SAR and pipeline, right? We have more number of digital bits at the output, but the effective number of bits is smaller. That is, if I apply a sinusoid, find the signal to quantization noise ratio, that will correspond to a smaller number of bits. Okay.
It is a more bigger challenge in designing this filter than.
Actually, no. This digital filter is pretty straightforward, right? See, you can get the impulse response in one shot in MATLAB, right? And then you just need to do one simulation. You truncate basically you have to round off this guy to some precision. Once you know how many bits you have to truncate it to, it is simple. I mean, the operation you need to do is pretty trivial, right? Just need to have one map block, multiply and accumulate, and you are done. So this is actually trivial. Designing it is trivial, but you should know how to design it. That's what I explained. You have to allocate sufficient number of bits to represent the impulse response. Okay. Cool. So this is the deal. So hopefully now at least qualitatively you are convinced that by choosing a large oversampling ratio, I can increase my SQNR, right? So now let's actually quantitatively estimate how much is the improvement we can get. So I am interested to find the quantization noise power within my signal bandwidth. How do I find it? I am trying to find the quantization noise power after noise shaping within the signal bandwidth. I have to take the area and from 0 to pi by m, right? So here it computed from 0 to pi. Now I have to do only to pi by m, right? So let me copy this. So I'll just say I'm finding the quantization noise power in band, meaning within the signal band. That is integral of 0 to pi by m delta square by 12 pi magnitude of this guy whole square d omega. Now remember that I am going to have a large value of m in practice. So my signal band will be really small, right? So for small values of omega, how can I approximate this guy as? We already saw. Omega square. So within my signal bandwidth, I can basically approximate it like this. Let us say delta square by 12 pi comes out. So what does it simplify to? Simple integral, right? Omega square.
Pi cube pi by m to the whole
Yeah, pi cube by 3m cube. Fine. So yeah, great. So now you see that if you choose, let us say m value of, I don't know, 10, this goes down as 1000. Okay. And now let us say I have chosen some value of m and I get some SQNR. Now let us say I increase m by 2x. What will happen to my in-band quantization noise power? It will reduce by 8x. So how many decibels will it correspond to? 8x reduction. How many dB reduction it corresponds to? No. 2 times reduction is how much dB? 10 log 2 is 3. So 9 dB. I mean 8 is 2 cube, so it's 9 dB. So it will mean 9 dB reduction in noise power, or I will say 9 dB increase in SQNR. If I am gaining SQNR of 9 dB, how many bits I have gained? Remember SQNR is 6 times the number of bits. So how many bits I have gained now? 1.5, right? So increases by 1.5 bits. So this gives a nice, technique. So you don't have to do anything. You just have to oversample it, right? And if you keep increasing this oversampling ratio 2 times, you simply sit and gain 1.5 bits of extra precision. Right? And the price you pay is you have to go and sample it at higher and higher speed. So this will work for small signal bandwidths. Okay. Cool. So one more thing let's look at. Yeah, so let me copy this maybe. So I'll make the observation here. If I increase m by 2x, my E knob increases by how many bits? How many bits? 1.5 bits, right? So this is if I do oversampling and noise shaping. Now remember, I can just simply do only oversampling also, right? So let us see what happens. So what I mean by that is this. So I have my input signal that has a bandwidth of fs by 2m. I just oversample it at fs and quantize it as usual. I don't do this noise shaping. So to refresh, we got this benefit by doing 2 things, right? One was noise shaping, of course, and second thing is we restricted the signal bandwidth to small value. Now what I am saying is I will do only the second portion. I mean, we are sure that only noise shaping will not help us, right? Because if I do only noise shaping, This entire thing is going to be my signal bandwidth, and this entire noise power we already saw, it was much higher. So only noise shaping is not going to work. We have to do it along with oversampling. Now the logical question to ask is, what if I do only oversampling, right? So let's look at that. So again, let me draw the spectrum. Quantization noise is white from 0 to pi. When I do oversampling, I am going to restrict my signal bandwidth to. So the area of this guy is what? Delta square by 12. So what is the quantization noise power in the signal bandwidth alone?
12.
Yeah, so I'll say NQ in band is delta square by 12. So here again I have assumed that I am filtering off these guys, right? So I have to go and put a digital low pass filter here and then downsample. So obviously if I did noise shaping on top of it, this went as m cube, right? So here we saw it goes as m cube, here it only goes as m, and that should also be, qualitatively that should make sense. Cool. So here if I increase the oversampling ratio by 2x, how much will my E knob increase by? 0.5 bits. So the summary is this: we can also just do oversampling without doing anything. In that case, you do get some improvement, but that improvement becomes much better if you also do noise shaping. Okay. So to summarize, what we do is this: I have the signal, I oversample it at a rate fs. This does oversampling, and then for noise shaping, I do this: I take the ADC, get the estimate of the, not estimate, we find the quantization noise by first converting it to analog and subtracting it, and then I go and subtract it from the input. Okay, it's okay. And remember that I cannot simply stop at this point, because this just shapes the quantization noise. I also have to what? After noise shaping, what should I do? I have to filter the out of band noise. That is the second important thing to do. So this all assuming that I am going to put a low pass filter here. It's a digital low pass filter, and then I downsample. Okay. If I do that, to refresh again, the output I get in the Z transform will be the input plus Q of Z into, what did we get? 1 minus Z inverse. So this way we can get a first order noise shaping, and it's basically high pass shape, right? So now some terminologies for you to remember. So let's say I say it 1 times Q of Z, right? So that this thing that multiplies the input is referred to as signal transfer function, abbreviated as STF. So this thing that multiplies the noise, what will I call this as? One is signal transfer function. Yeah, it's matter of fact, no complications there. Referred to as NTF. So the deal is this: you the idea of noise shaping is this, right? Instead of having the quantization noise flat, you first oversample it, and then you make sure that the quantization noise passes through a noise transfer function that makes sure that the quantization noise around the signal band of frequencies is greatly reduced. In this case, the signal band of frequencies is from 0 to something, but it can be any other band also. And once that noise shaping is done, you can have a digital low pass filter and remove the noise outside your band. Okay, cool. So this is the basic idea of noise shaping. Now what I get is this, right? So let me write that here. V of Z is Q of Z plus 1 minus Z inverse times Q of Z. Now this is what I need, right? Now once I know what I need, I can make multiple circuits and multiple systems to realize the same thing, right? And just like how all Fast and Furious movies have the same story, all like movies have the same stories, right? So this error feedback thing is one way in which we can do it. There is also one other powerful and very popular way in which we can do this. And to come to that architecture, let me actually rewrite this equation slightly. I'll divide on both sides by 1 minus the inverse. And then I'll bring this guy to the right. So I'll literally bring it to the right like this. Directly written it. This is 0. Now of course I want the left side to be output, so I add V of z on either sides. Okay. So if I simplify this, what do I get? Can you simplify and tell me? One second, let me try and put it here in one equation. Just simplify this portion. What do you get? The u of z is there, and then minus z inverse by 1 minus z inverse. Basically it all gives this guy, right? I have just massaged that equation to get something else. So now let's try to make a system that realizes this. Okay. So I have the input u, I have the output v. So what am I doing to the output first? Z inverse is there, and remember output is digital, so actually I'll have a DAC here, and then say I have Z inverse, and then what do? I have this, I have to subtract these two. Then what do? I have to give to this block, which is the integrator, you guys know already. Delay free. And then I have to add quantization noise. I just put an ADC. That will add quantization noise for me. So in practice, we can do one more modification is done to simplify the implementation. Okay, or first let me write it here. Here I get V to be U plus Q times 1 minus Z inverse, right? Same thing. Remember, I started from this equation, I just modified it in a slightly different form, right? So it's all 1 plus 3 is 4, 2 plus 2 is 4. Final result is 4, right? So let me push it to next page. Cool. So in practice, one other slight modification is done, which is this. So instead of directly feeding the U, let us say I delay the input also by one sample. Okay. Let's say I do this. So what will change in this equation? Initially I was just feeding U. So now I am feeding, what is this here? U times Z inverse. So only this guy changes to Z inverse. Now if I do this, I see I have 1 Z inverse here, 1 Z inverse here. Both can be pushed in and brought here, right? So let me actually draw this. It's very slow. I'll draw the duck here nicely. And instead of this being 1 by 1 minus the inverse, it is your delayed integrator. So now the signal transfer function is this, NTF is the same. So this guy, let me again take it to next page maybe. Yeah. So this guy is called the delta sigma modulator or DSM. Delta is because you are taking the delta difference here. And what is this guy? What operation does Z inverse by 1 minus Z inverse do? It's an integrator, right? Integrator is accumulation, so sigma, so delta sigma. So, and this is the first order delta sigma because we have because there is only one pole here. Okay. So again, you see that this is basically a negative feedback loop, right? Again, you can also come up with this architecture following the same logic we had for our calibration loops, right? So what we can think of it as like this. I have my input U. Let us say the ADC is digitizing and giving me something. I want to make sure that my output is close to the input. So what do I do is I'll convert to DAC first. I'll form an error signal. I want this error signal to go to 0. If I want the error signal to go to 0, what do? We put an integrator, and that's what this is. Okay. So again, this negative feedback loop is the underlying thing in almost everywhere, right? And if I do this now, you should be able to tell what is the DC here. If I look at this signal, I call it some, I don't know, I'll call this error signal E. If I look at the average or the DC of E, what will this be? It will be exactly 0, right? So which means, if let us say at the input I give a purely DC input. Here the output of the DAC is, let us say, B. What can you say about the average of the output? It will exactly match the DC at the input, right? So now from here you can see, right? If I give a DC input, at the output I have a digital data whose average exactly matches the input. There is absolutely no error there, right? So I have kind of eliminated quantization noise at DC, right? That should also be clear if you remember the spectrum of quantization noise, right? So this is the quantization noise spectrum after you do noise shaping. At DC it is 0. Okay. So which means if let us say I give something, let's say the input is some 0.351 volts or something. At the output I'll have a stream of ones and zeros here. Let us say 1 0 0 something like this. And once it passes through a DAC, this will convert to some 0 to some VREF. And if I look at the average of this, that will exactly match 0.351. If you make it 0.35145, this will exactly match 0.35145. And we remember that we have a low pass filter here, right? Usually, this low pass filter can be thought of as taking this average for you, right? So again, I just wanted to appreciate that everything here is based and built out of negative feedback. Okay. Okay, then maybe, yeah, if this is clear, maybe yes, right. So let us say we have some circuit containing only resistors and capacitors, nothing else. I gave some finite input as some input which is finite. Okay. There are multiple capacitors. Let us say look at some capacitor Ck. So what can you say about the average current flowing through the capacitor? Why? Yeah, so remember, what is the voltage across the capacitor in terms of its current? If I write in terms of time domain, if I know the current, 1 by C dt, right? If the capacitor has non-zero DC, what will happen to this? Why can't it go to infinite?
Because there is no other voltage which
Yeah, I mean, see, things should not be half-assed, right? We should try to reason it to the fullest extent possible, right? There is no, I mean, you can't keep asking why for everything, but at some point you should be convinced. It makes sense that, I mean, if this has a non-zero average, this voltage will blow up to infinity. The question is, why can't it blow to infinity?
Because to match the KVL,
Not necessarily.
if there is something infinite, there has to be some other. Make it zero. You invite to infinite.
Okay. Let's say if there is something that goes to minus infinity, that will cancel it, right?
Infinite minus infinite.
I mean, it's not infinite, right? I'm saying one is growing this, one is growing like this. I mean, see, if remember the input I've given is a finite input. I'll say it's a bounded input, right? And this network, as I told, consists only of R's and C's. Can this be stable? I mean, can this be unstable?
No.
It cannot be unstable, right? I have only R's and C's. If I look at all the poles, it will lie on the left half of S plane. If all the poles lie on left half of S plane, it is definitely stable. For stable input, if I give a bounded input, output should be bounded, right? So here you are making an inherent assumption that the system is stable. Right? I mean, actually, even if you look at a simple RC, right? I can think of it like this. Let us say VI and V out. What is the current flowing through this? Right? So I can actually model it like this. I have VI, I have V0. This is converted to a current. And once I know the current through the capacitor, how will I find the voltage? Integrate. That is basically a negative feedback. And here, remember that this is a first order system, so it's definitely stable. And even if you have multiple R's and C's, if you just have passive RC, it can never become unstable, right? That's the inherent assumption. So again, I want you to appreciate that negative feedback is everywhere, right? I mean, the simplest example I give is this, right? I don't know if I already told this to you guys. I mean, let us say you are listening to songs in your headphones. You might have noticed, right? If you are listening to songs in like proper headphones, you tend to speak out loud.
Yes.
And why that happens?
There is no proper negative feedback.
Yeah, not that. So if you think about the way your brain functions and how you speak, your brain knows that I have to speak at some level, so that it's not very loud. It is audible to the opposite person. So you are the speaker here. So whatever you speak, your ear hears it back. Yeah, and your brain sits here and instructs saying that whether it's correct or not. Now the moment you put your phones, what happens?
There is a problem with hearing back.
Basically, you are not hearing the entire thing back. Only attenuated version comes here. Right? Let's say that's 1/100th of something. So let us say V out. So the negative feedback will try to make this signal equal to this signal. So my ideal level will be V out by 100. You will tend to shout 100 times higher. Okay. It's all the same. Cool. So let's come back to this. We digressed a lot. Yeah. So the bottom line is the same noise shaping can be done using this negative feedback loop, and this is even more powerful. We can look at the reasons in the next class. So I'll just show that once again. So we have the input, and then we have the integrator, we have the ADC, we have the DAC, and then we do this. So, and the output we have a low pass filter and downsampler. Okay, that's right. And here if I see the signal transfer function, remember signal transfer function is basically the output by the input when my quantization noise is 0, right? You can basically model it like this. Similarly, my noise transfer function, what is noise transfer function? I mean, signal transfer function is basically the transfer function signal to the output. This is V.
V upon U when
V upon?
U.
No, it cannot. I mean, noise transfer function, right? I am trying to find the transfer function from where to where.
That's okay. U upon Q and Q equals to 0.
Basically, if I find the output, I will have something multiplying the input plus something multiplying the quantization noise. This thing that multiplies the input, this is U, this STF, This thing that multiplies the quantization noise is NTF, that's all. And this is a first order modulator, and what is the NTF we get? The quantization noise is filtered by 1 minus the inverse. Okay. So basically that gives us some reduction in the quantization noise. So let's say, or maybe I move to next page. So right now we have 1 minus the inverse. So basically it does something like this. Now I can get greedy, right? So 1 minus the inverse is a first order high pass filter. What is an even better high pass filter? Yeah, second order high pass filter. What is the simplest second order high pass filter? I mean 1 minus the inverse is first order high pass filter.
1 minus the inverse minus the 2.
No. I mean simple, right? Don't think complicated. I have one filter. I want to make a higher order filter. What is the simplest thing I can do? I can put one more here, right? So I can basically have square. So that might hopefully give something like this. Maybe I'll not draw it like this. Let us say something. Now I don't have to stop, right? Let's say I do per 1000, maybe not 1000, let's say 100. Then I can get really small noise here and attenuate everything else. So what is the issue? Huh? So the thought process is clear, right? I have first order. The first order high pass filter reduces the quantization noise within my signal band of frequencies to some extent. I want to get better. So I try to have a higher order high pass filter. The question is, why can't I keep increasing this order and get, let us say, a 100th order high pass filter and do it? Or let us say first let's come to this. To get 1 minus the inverse, the block diagram I have is this, right? Let me quickly draw the ADC. I'll not draw the DAC, or maybe I can draw the DAC, it's okay. Now let's take one step first. I want 1 minus the inverse whole square. What should I change here to get 1 minus the inverse whole square? I don't want what exactly has to be changed. Which of these blocks here has to change? This integrator must not be an integrator, it should be something. I'll call it some general L of Z. Okay, and this is often called the loop filter, again for obvious reasons. Now tell me, here I have this B. If I find the signal transfer function here, what will that be? Signal transfer function is the output by the input when the quantization noise is not there, right? So essentially this is a straight line now. L by 1 plus L, right? Standard negative feedback. Okay. So this is going to be L of Z. Now remember, for a first order, oops, I have to write it again. Now for a first order noise shaping, what was L of Z? Z inverse by 1 minus Z inverse. So if you have a, let us say, second order, how many integrators I should have, do you think? At least 2 is required, right? So if you have integrator, what can you say about the gain of the integrator at DC? No. Infinite, right?
Infinite, yeah.
So basically at very low frequencies, what can you say about this value? Close to infinite. So this entire thing, what will it approximate to? 1, right? And remember, we are looking at signal frequencies which are low. So within the in band, I will say approximately it's 1. Let's look at NTF. NTF is the transfer function from the quantization noise here to the output when the input is not there. So what is the transfer function? Again, remember that you can work it out in any way. So this is not there. I'll find the forward transfer function from here to here. The forward path is just 1. You can work it out divided by 1 plus 2k. Is what we do.
Yes.
Okay. So now let us say you want to get some particular NTF, we can choose what my L of Z is. Right? For a second order, you can work out what this is. Now let us say you keep increasing it, and let us say you want to have 100th order NTF. What will happen?
This will go to 0.
Now let's write it, right? So if in here it will be L of Z is 1 by NTF minus 1, right? From here. If I want to have a second order noise transfer function, what should be the order of this filter? Should be second order. If I want to have 100th order noise transfer function, what should be order of this? So what's the problem? I mean, let us say it's a regular negative feedback system, right? So think of what you know, right? Let us say this is your standard negative feedback loop. You guys know this properly. So here I have L of Z, let us say. I keep increasing this order. What can go wrong? Remember, if I keep increasing the order, this guy will have more and more delay, right?
First answer is correct.
If we keep increasing the order, we'll have more and more delay. I mean,
Yeah.
simply because see, if you think of it in continuous time, first order will require one RC, loosely speaking. Second order will need one more set. So we'll have more capacitors, more delay. And if you have lot of delay negative feedback loop, what can happen? It can become unstable. So this is what happens in a linear time invariant network. But here it is not LTI because we have this quantizer. But whatever you guys hypothesized is true. If you keep increasing the order of this guy, this thing can become unstable. But how it becomes unstable is slightly different. So we can actually continue from that point in next class.
And you are